Probably most of you were at the keynote already. You kind of know the subject. The purpose of this talk is to provide a more kind of in-depth introduction and explanation of what we're up to and what this is about. So the talk is divided in two parts. In the first half, we're just going to talk about what reactive programming is from the perspective of a Java developer. So we're going to take a unique perspective of really trying to do something very straightforward, which is to design a Java API in an asynchronous, non-blocking way, and then see where we end up by doing that. And then in the second half, we're going to talk about applying this to web applications. And that's where we're going to talk about Spring 5. So there's this long-running shift to concurrency. Probably many of you remember this book, which published in 2006. And one of the things that the book talked about, and of course that was the time when we got a major update to Java util concurrency. We got a whole bunch of thread pool implementations, atomic types, and so on. But one of the things that the book talked about was how we were at the end of Moore's law. Which means that we're no longer getting a free lunch from the hardware, improvements from the hardware, and that from now on it's going to be about Amdahl's law, which is a law that has to do with concurrency and multiple cores, and how the amount of synchronization that you have in your application, even small amounts, can have quite big effects when you start to replicate on multiple cores and run in distributed fashion. In other words, it was going to be about applications doing more, about becoming concurrent and being concurrent more effectively. And back at the time, I really wondered, what does this really mean for us as Java developers? Because here we are, at the time with Java 1.5, and we got thread pools, and that gives us concurrency. What else is actually going to happen dramatically? And it wasn't until a few years later, when Node.js came out, that kind of the story began to make more sense. And Node.js, of course, they had a natural constraint where they had to do the same things on the server side without the benefit of multi-threading and having multiple threads. And it's interesting that it was Node.js that kind of demonstrated what you can do with a single thread, the kind of level of efficiency that we would think unimaginable. We almost kind of assign a little superpower to multi-threading. But actually, if you use it properly, you can do a lot with a single thread. Now, in Java, we actually have already, have an ecosystem of libraries and frameworks where we do a lot of the things in imperative style logic, where we do concurrency in places where we really have to. It's more the exception than the rule. It's a very different situation than the problem that Node had to solve. So naturally, as a result of that, there's a lot of inertia in Java. So as soon as Node.js was out, it doesn't mean that we're going to change things overnight, because these kinds of changes are very deep and they take a very long time to happen. But I would argue that the reason why this is actually entering the mainstream, it's not that we haven't been trying to do non-blocking in Java. There's a lot of examples. But the reason why is because a lot of things have changed about the way we build applications. So 10 years ago, our applications were much more self-sufficient. We would deploy to an application server. And the basic rule of thumb was keep things simple, don't distribute unless you really have to, which is still a good principle. But what we have today is a very different situation. We have we're deploying to a cloud environment. We're looking to break the monolith into microservices, and those are independent of each other. And they need to communicate with each other, which introduces automatically a level of kind of loose coupling and interconnectedness that implies latency. So in order for us to achieve the same things, we now almost by default require to deal with latency much better. And of course, we can do a lot with thread pools, and we can do a lot with asynchronicity, but the fact is that if your application, if you're not ready for this style of writing logic, dealing with non-blocking, imperative logic, and we'll see what I mean in a little while, by imperative, but it's basically what we do today. When you write your algorithm top to bottom and more or less a single call stack assumption, everything happens in the same call stack. But when we have to make asynchronous calls, even within this model, let's say we use an asynchronous HTTP client. We make a call and then we're called back when the results are available. Well, the more of that we are forced to do, the more we have to deal with asynchronicity no matter what. So even imperative logic is no longer simple, as we have to deal with more and more asynchronicity and more latency. In addition to that, and this is something we've already known for a long time, there are limits of scale in what you can do with imperative style logic. We talked about this in the keynote, how yes, it is possible to scale, but certainly it takes more resources and it's more expensive, and ultimately it's less predictable what happens on any given day, because we really depend on the latency and the kinds of clients that we're dealing with, fast versus slow. Now, reactive applications is about fundamentally non-blocking and event-driven architecture. This is about introducing this into application design, and it's also about using a small number of threads to process potentially many concurrent requests, and also about having some kind of flow control, because when you deal with an event-driven system, you have a publisher-subscriber relationship, a producer-consumer, and then there's always situations where the producer can produce more than the consumer can take. So we'll talk about introducing some kind of control boundaries and queues that can help to manage this and push pressure further upstream so that we can communicate to the upstream that we're not ready to consume more. And by the way, if you go back to that book, Java Concurrency in Practice, even the book at the time talked about this very capability. And some of it is built into thread pools in Java. You know, there's a way to configure the thread pool with specific strategies, but it's very limited in terms of the ability to communicate this across an entire pipeline of components. Right? So we can choose different strategies to reject threads, to stop receiving requests. We can create a pool, and we can say, okay, if we're dealing with too many requests right now, the thread pool can grow a little bit, but eventually, you know, that's not enough. We need more ways to deal with high volumes. So that's basically taking that same idea much farther. Can you say that a little louder?
When you say push pressure further upstream, doesn't that mean like a more memory consumption on the back end or something? Aren't we risking like
Ultimately, so the question is, does it mean more memory if you push back pressure upstream? I'm only doing an introduction, so we'll come back to this a little bit later. But in short, generally the impact is consuming a lot less resources. You are creating some queues in order to queue things that, you know, as we're prefetching data before it can be processed. But overall, the impact is reducing the amount of memory that is being used because you don't need as many processes to scale, you don't need as many threads, and so on and so on. But we'll come back to that. So let's start with a very simple task. Let's take a user repository the way it might be written today, and see how can we change that to become asynchronous and non-blocking if we enter into this world of, if we accept that we want to become non-blocking. How do we do that? So the first idea might be that, and this is the usage of that repository. This is what we mean by imperative style logic. We invoke the user repository, and then when the user is back, we do something with it. If there's an exception, all of this happens within the same thread. It's really easy to write this logic. It's sequential. There's no additional callbacks to deal with. But it does mean that if there's any latency introduced by the repository, that impacts our overall processing time. We're blocking the current thread for that. Now, let's replace that with a future. And we also have to take out the exception from the declaration, because that may come from a different thread. But the problem with futures is that there's really not much that you can do with it when you really start using it in multiple places. So if you just make a single call, eventually you'll need to get the value. But if you have multiple calls and you have interdependent asynchronous calls, then you're stuck waiting for the first one to complete, because you have to say get and then use the result of that to make the next call. There's no way to compose that logic up front without blocking on any one of those features. So ultimately, the Java future isn't really non-blocking. Now, we do have completable future in Java 8, and that's where things become a lot better, because the completable future gives us a declarative API, and this is what I mean. You can see that method when complete. We're not trying to get the value. What we're saying is, here's a lambda expression that describes what should happen when the value is actually available. We're now composing asynchronous logic. And you can imagine, if you compare this to the imperative style logic, imperative is all in one place, and you can read it from top to bottom. Here we get a very similar effect. It's not nested through callbacks, but you're saying when complete, and then you declare the logic, and you can almost see the same thing, but it's broken out into chunks of code. That's really the effect of using a composition API like that. And there are other methods. If you haven't seen completable future, you can further compose on top of that, and you can keep creating kind of a pipeline of things that should happen when things complete. And that's the idea of using such an API. Now, our repository also has a method to return a collection of users. And our first instinct might be to wrap that as a completable future, which certainly will work. And also, we have a save method. And you can see here that instead of returning void, we're returning a completable future of void, because we actually want to know when that operation is complete, so we can compose some further logic. Remember, we're no longer doing things imperative style. We now have to continue with what we're doing after that user is saved. Or that will communicate an exception back to us, just the same. So completable future is fundamentally the right idea. It's an example of the kind of API that we want. It lets us declaratively compose asynchronous logic, so it still remains readable. We can use lambdas with Java 8. That's a big helper, and makes the code very readable. But the problem with completable future, it's really not ideal for dealing with anything more than a single value. So wrapping a collection of return values kind of works, but not really for any latency sensitive data sets, if some of the values may not come immediately, right? Using a collection kind of implies that you're going to get all your items and then you can work with them. But it also means that until you get all the items, you're not going to get anything. So it's not an ideal way to deal with, to work with multiple values. Certainly not a good way to deal with infinite data sets. There's just no options for that. We really want something that represents all of these cases. So we're back to the drawing board. What can we use? So here I'm going to inject an idea. What if we represent return values as a stream? Let's say we did some brainstorming and suddenly this brilliant idea came up. That instead of dealing with, just like we do with the completable future for one value, what if we do that for a stream of values? So each time we have one callback for each item, and then in the end, we complete with error or completion notification. And that works really well because now we can represent all of the cases using a single mechanism, a single kind of abstraction. You can see here from top to bottom, the first two rows are the void methods, that's the save. Then the methods, the next three rows, returning a user, a single value. And then at the bottom, a collection of values, just working with the API that we have, that we started with. And you can see how a stream of notifications can represent all of these cases in the same style, in the same mechanism. So for the void success, we just get a complete notification. There's never a value that will come there. Or we get a failure. For a single return value of user, we're going to get that value or incomplete, or maybe we're going to get an exception before it completes. And then if we have multiple matches, we're going to get one notification for each matching user as it becomes available. And then when it's done, we're going to get an incomplete notification. So this is an ideal representation of all the possible outcomes from asynchronous call and dealing with those return values. Now, Java 8 Stream is actually a good example of this. It has even more of what completable future provides, but for a stream of values. It gives us, again, declarative composition for asynchronous logic to be applied on each individual item of that stream. And once again, we can use lambdas to keep things readable. It looks beautiful, but Java 8 Stream is, of course, built for collections. You can only use a stream a single time. You obtain it from the collection. It's usable a single time only. And it's really not for any kind of active or hot source of data, something like emitting stock quotes or emitting some kind of alerts, something that doesn't necessarily all come together. It doesn't get combined as a collection, or maybe even infinite data sets. And again, this is from the initial announcement from Doug Lee of incorporating reactive streams into Java 9. That does not mean that we're waiting for Java 9. Reactive streams as a specification was completed about a year ago. It's at version 1.0, and it was created through a collaboration of multiple companies, including Netflix, Pivotal, Lightbend, and a few others, Kazing, Twitter. And basically, they created an API for asynchronous components to interact with each other. And this was actually picked up by Java 9, so it will be included in Java 9. There's a flow class in Java util concurrent where all the contracts will be. And there's some questions around why should this be in Java 9? I mean, what's the point of just including a few interfaces? And if you follow these links and look around the mailing list, you'll see some interesting debates around that. But basically, the position of Doug Lee is that even the JDK, Java needs something like that, an API to serve as the basis for these kinds of things, even if today it isn't incorporated in any specific areas. My take on that is that basically this was included rather late in the cycle for Java 9, so they didn't have time to properly introduce it, but that's the intent. They want to get it in, and then it will be in various places. The only thing that will be in Java 9 is a implementation of a Reactive Streams publisher called Submission Publisher, which is basically a bridge to Reactive Streams. But you can see places like HTTP2 client, also places around NIO where things can be done with this. But in any case, it's important that this is getting included in Java 9 as another assertion of the importance of Reactive Streams. Now, Reactive Streams, again, is a small API that includes 4 small interfaces. There are some specification rules around it and a TCK. It's completely open. And it's about a publish-subscribe relationship between 2 components with backpressure. That's the main goal, the main purpose of existence for that spec. It's in fact quite refreshing to have such a small spec. These days you don't come across that very often. The spec is focused on interoperability across async components and libraries. It's really not meant to be used very directly by applications. In fact, it's quite low-level interaction between components. But we'll come back to that. This is an example of, this shows you the main interfaces. You have a publisher and a subscriber. And when we have a subscribe between a publisher and a subscribe, the subscriber receives a subscription. And the subscription gives you 2 methods. You can see the request and the cancel, which provides the basis for the backpressure. So you can request more items or you can cancel. And what it means, what the number n means, is really left unspecified. Basically, the idea is that you can say, give me 5 more of whatever you've got. And then when you get 5 more, you ask for more. So there are different strategies for how you can go about it. But the idea is that you have a form of flow control. So for example, for an HTTP connection, you might be dealing with data buffers. There's nothing in the specification that says how big the data buffers are. There's no such calculation, how many bytes are we talking about. We're simply talking, you give me 5 more, and then once we're done processing those 5, I can ask for more, and different strategies around that. So that's intentionally left a little bit unspecified. Now, as I said, Reactive Streams is a pretty low-level contract. This is why we have reactive libraries in Java. And Project Reactor is actually the library on the JVM currently, very close to GA, maybe a week away from it, but currently release candidate. The library for the JVM, essentially, at the moment, for working with Reactive Streams, so it gives you all the infrastructure you need. And it's actually quite hard. It's really not simple to just go off and implement publisher and subscriber. Well, subscriber is easier because you're just consuming, but on the producer side, you have a lot of responsibility to deal with asynchronicity. And while it can be done, it's really not something you want to do in most cases. So Project Reactor gives you that foundation. But it also, very importantly, it gives you the declarative operations that you need on top of that in order to actually compose your asynchronous logic and be able to take advantage of backpressure. So that's what the Flux and Mono reactive types are. They're a functional API. Each of them has quite a number of methods. That's quite common in functional APIs. It's a little bit different than using, for example, object-style API where you expect a certain number of methods. But Mono and Flux are really the main API that you use to compose the asynchronous logic. Mono is really just a variation to deal specifically with data sequences of 0 or 1. And this is similar, comparable to completable future, how you would think about using that. And we Reactor didn't start out with both of these types. Initially, Reactor had only Flux. And of course, Flux is the more general representation of a stream of any number of items, including 0, including 1. But we found in our experience in building Spring 5 that it's actually very useful to know in many cases from a framework perspective whether we're talking about a stream that's going to produce at most 1 item or whether we're talking about a stream that's going to produce many items. So for example, if you're serializing JSON, if we know that your controller returns a mono, then we know we're only serializing 1 item, so we know what to do from there. Or if we're consuming the body, again, that helps us a lot to know, are you planning to consume a flux of items? In other words, kind of a streaming scenario, or is it going to be a single thing that we can just read, which is the majority of the cases? So we have both Mono and Flux. They have their own operators each that apply and are specifically designed for whether you're dealing with a stream of 1 or a stream of many. So this is what the reactive repository would look like. We can now introduce the use of Mono and Flux for the return values, and that gives us something back that we can compose logic on, and something that also allows for backpressure to be communicated to components that are actually consuming this data as we create an entire pipeline. This is an example of using it, using the repository. So you can see here that after invoking find all, we can do operations like filter and map. In fact, this looks a lot like the stream API in Java 8. And if you create a similar example with a collection, it will look identical. But here, of course, we're talking about something more because we also have backpressure. And furthermore, the Flux type in Reactor has a lot more options and deals with scheduling and time-related operations. So it's really different in scope and purpose, even though on the surface it looks quite similar to the Java 8 API. The thing to keep in mind is that when you're invoking filter or map, and this is similar to the Java 8 Stream API, nothing really happens. So this is one big shift between imperative and non-blocking reactive style programming, is that you have this initial phase when you're declaring the logic. So for example, when a web controller gets invoked, you can compose all the logic, but the logic is not actually going to execute. That's the thing which is inside the filter, inside the map, until you have a subscriber. And that usually happens after you return from the controller method when the underlying framework subscribes, and now we start reading from the HTTP request, writing to the body, and so on. So really initially we're composing the logic, and then when we subscribe, that's when the data begins to flow. And this is the output from the log operator. You can kind of see the Reactive Streams protocol in action. First, we have the subscribe. It's at that point when things begin. Then, in this case, because we didn't specify anything explicit, we just subscribed, what happens is that we request unbounded, meaning the actual value for that is long max value. In Reactive Streams, that signifies that you want all the data to be sent to you. You don't want to impose any flow control. And so we start to get the data, and eventually we get an on-complete notification. But we could do things like use capacity, and that is a strategy for consuming 2 items at a time. So we can start to apply things like that. And what you see is an unsubscribe, and then we're requesting 2 items, and then as they come, it's a little actually difficult to get a realistic sense of how this works, because if you're thinking about a completely synchronous scenario, this looks like cheating a little bit, like what's the difference? You know, you're asking for 2 items at a time, but they all still continue to come. The difference really comes when you start thinking about this being asynchronous and happening on different threads without blocking. So the producer, for example, may produce items on a given thread, which could be, let's say, the runtime, the tomcat or jetty, that we really don't want to block. Then when we take that data, if we make a non-blocking call to a microservice, that again is going to happen in a separate thread. And really we can get to the end of the 2 users, and then there could be a period of time when nothing is happening. And until we request more, we will not get any more data. So that's really when you begin to imagine more concretely how useful this is and how differently that works. The kind of control that we begin to get. Yeah, and actually, any questions so far? I see one there.
So, a question, 2 quick questions. Which version will we first see the Reactive API on SpringData?
In SpringData. So the question is, when will we first see reactive support in SpringData? That's the upcoming release. I believe it's called Hopper. If you see, the slides were already published from yesterday's talk on Twitter. If you search for that, the intro to SpringData, what's new in SpringData.
Follow-on question.
Yeah.
You should think about the capable support that currently resides within SpringData and SpringData REST. How is that going to morph with these kind of constructs?
It's a good question. I actually don't know the answer to that. So it'd be interesting to take a look how that's translated. Do you have an answer to that, or another question? Okay. So I'll have to defer the question. I don't know the answer. Hi. In the context of SpringData? Okay, so the question is, how would it support protobuf, and what were the other ones? Aaron, yeah. I'm not sure that that necessarily belongs on the side of SpringData. I think, well, first of all, Reactor has Aaron support. That's more of a kind of a network-oriented Reactive Streams translation. So there are a number of different reactive initiatives. There's Reactor Kafka. Within Reactor, there's a Reactor I/O module, which translates Reactive Streams to Netty, for example, both client and server side, and we use that actually in Spring 5. There's also support for Aaron, etc. As far as protobuf, that's probably something we're going to support in SpringWeb. We just haven't done it yet. But
how would this work with transactions? Say, I mean, would a transactional annotation still go?
No, at the moment, there's no support for transactional annotation in the context of this. We're still, looking at options. There are some ideas that are floating around. It's not an easy question to answer. One possible answer might be that there is no good equivalent, that maybe it might mean that we move away from relying on transactions in the way that we have in the past. Like if you look at Mongo and other data providers, they have kind of a different perspective on transactions. But this is still up in the air, I'm just being completely honest.
Is there any typical case or what size fits most for backpressure? What is the process of determining or identifying how much backpressure you're going to need? How does the developer make that decision?
Okay, so the question is, how does a developer make a decision about backpressure, and what's a good example of where it would apply, or an example of how you would implement it?
I guess, is there a standard case or something like some backpressure case that fits 90% of situations? Like how much time and effort is going to need to be spent tweaking backpressure configuration?
Yeah, how much time would be spent with backpressure configuration? There's a bit of danger always in introducing so many new concepts. Really, and thanks for the question. What I can clarify is that really, from an application perspective, very often you're in the middle between the producer and the actual end consumer. So if you're writing, for example, a web application, what you're doing in the controller layer is really you're connecting the dots. You're making a microservice call, or you're calling a data repository. You're almost not very often going to deal with backpressure explicitly. That's something which is just going to propagate. There may be configuration that will be exposed, for example, at the HTTP runtime layer on the Spring side that allows you to pick maybe different strategies of how you deal with it. But ultimately, it's something that's more of an underlying mechanism that we explained here because it's so central and so important. But it does have the danger of becoming more important than it will actually be in your face in your day-to-day development.
So is that to say it'll be mostly built into the drivers, or
It's mostly built into the libraries providing this kind of capability, and we're going to see in a moment some examples with SpringData. Yeah. Okay, so moving on to the second part, reactive web applications. So far we've talked about how to transform our user repository from an API perspective, and we arrived at this place. But now the question is, how do we actually implement this repository? What do we do inside of here? How do we actually make that work? Well, there are multiple options. First of all, you may have to use a blocking library and a thread pool, in which case you may wonder, what's the point? Isn't that what I was doing before I started? Well, one advantage that I can point out is that for those who are using the user repositories, it allows them to start working in a reactive manner. So it gives you an API to interface with something that may underneath still be blocking and requiring a thread pool. But nevertheless, it allows you to start using a different way. And then sooner or later, you might be able to replace it with an actual alternative. If you have an asynchronous library that you can call, then that is another option. And it is possible to translate into Backpressure. It really helps if the library actually provides ways to ask if you can do this or that, like reading and writing for I/O. But as long as the library is asynchronous, there are things that can be done. And then the ideal case is if you actually have already a Reactive Streams ready library that provides you with backpressure. So then you don't have to build such a bridge. And this is why with SpringData, it makes such a big difference because your job is already done. You don't have to do anything further. So this is an actual example from the SpringData talk that was yesterday in What's New. So you can check out the code for that. If you track down the session, they already published their slides. And there's an actual code repository with this, and you can see the person repository, which typical SpringData style, you create an interface with methods, and then those methods are implemented. And what's really nice about SpringData is that it lends itself very naturally to using whatever reactive library you want. So we haven't talked much about RxJava, but I'm sure, how many of you are using RxJava actually? Okay, I see a few hands. So if you're using RxJava, that's supported already by SpringData, and it will be released not far in the future. You basically implement your repository using the reactive library that you want, and you get that result. So really, at the end, what we want is that end-to-end backpressure. That's the ideal situation that we want to be in, and all of that works behind the scenes. We are provided with methods. We focus on composing logic, but the backpressure should work behind the scenes. So we'll take a look at some examples here. First, this is a reactive web controller. So now we can take that user repository that we transformed to be non-blocking. Now the next step is we want to put that into a reactive web controller. And then, well, this is step number one, right? So then we have to actually write some methods. So in Spring 5, we have full support for doing things like that. Here you have an example of each one of those repository methods being exposed through a controller method. All of that is fully non-blocking. And we can just return those types directly from the controller method, and they will be handled underneath. And again, that's a Spring 5 capability. You will notice on the bottom, the add user method is actually taking the user not wrapped in a mono. So if you have observed that, if you have noticed that, you may wonder, how does that actually work? Doesn't that imply blocking? It means that we have to have a user object before the controller method can be invoked. And as we are used to with the servlet API, you know what happens. You have a chain of filters, and then you have a servlet, and then we're invoking the controller. And if at that point we start to read the request body and we block on a slow client, then doesn't that mean that this method is going to block? Well, with the reactive support, this is done in a completely non-blocking fashion. That's underneath the foundation is non-blocking, and it means that we can support the same convenient method signatures without blocking. So what that means in short is that this controller method, the add user method, isn't getting invoked until the user is fully resolved. So you have a slow client, it takes a while to read the data. That's okay, because you're not going to get invoked until that's ready. And that doesn't incur any cost of threads. Question? So the question is, if the controller returns an observable, RxJava observable, will that get chunked? I'll come back to that in a moment. So let me just go through a couple more slides. That's a good question. Okay, so here is, first of all, an example with RxJava. You will notice that it looks very similar. RxJava has the single and the observable. The one notable difference is that the single type in RxJava actually means a single value only. There's no option for no value. This is a slight difference with mono in Reactor. And where this is less than convenient is, for example, when you have a request body, if you want to declare that as a single, that effectively means that that body is required. So you no longer have the option to say required is false, because single kind of implies you have to get a value, or else it's never going to complete. So this is where the monotype is a little more flexible, but with single, you can still declare it, but it has to be a required body. So in order to make this work, we have a SpringWeb Reactive module and also Reactive HTTP layer underneath. Again, this all works on Servlet 3.1 containers, Tomcat, JD, also Netty and Undertow, which is a new capability, obviously not something that was possible before. And one of the things that we have underneath, for example, is that we now we have abstractions that represent the body of the request and also the body of the response with Reactive Streams and actually using the Reactor library. So at this point, you may wonder, why is this Reactor and not Reactive Streams, for example, to keep agnostic to the Reactive library? Well, we actually started out with using Reactive Streams only in our APIs. And this was kind of the common wisdom, if I can say so, about a year ago. In fact, it still is on the RxJava wiki page. There's a page that talks about Reactive Streams, and there's a recommendation there that libraries should probably expose Reactive Streams in their API, and then on top of that, you have an application that can choose whichever Reactive library it wants. The catch is that as a web framework, we have to do some reactive work too. We have to compose some logic. We have to do many things for a web application to work, to resolve arguments for the controller, to handle return values. We're not just passing through, we're actually doing a lot of work, invoking JSON, JSON, serialization, deserialization. So we have to do some reactive work ourselves. And so for that, either you build your own reactive library or you use one that's available. So for us, it made a lot of sense to use Reactor because the Reactor project is also developed within Pivotal. So we've been able to work very closely on that with the current version, Reactor 3, coming up almost in the next week or so. And once we started using Reactor internally, that was step number 1 in realization, then it was kind of silly not to expose Reactor in the return values at least, because we already use it internally, so why are we hiding it? By returning these values, we're returning something that's still a Reactive Streams publisher, because Flux and Mono, they implement publisher. But actually what you get back is something that's instantly useful that we already use internally. So it kind of doesn't really make sense to hide it. And you can still see that wherever possible, we accept Reactive Streams as input, which means that on the input side, it can be any publisher. It doesn't even have to be Reactor. But on the return value side, we just expose what we have internally. And if you look at Ratpack and other examples in this space, you will see a very similar kind of outcome. Ratpack has its own Reactive Streams implementation. They're not using anything off the shelf. And it's suited for their purpose, for what they do internally. It's probably more limited than what you have in RxJava, but it's good for their purposes. So it's kind of the same idea. And then on top of that, we have Reactive HTTP Server Adaptation. Sorry, to make that work, we actually have Reactive HTTP Server Adaptation, which means that we have to translate and provide such a request and response on top of different servers. So for Servlet 3.1, it means that we have a bridge to Reactive Streams, and that's currently in SpringWeb. But I'll mention something else in a moment. We have similar integration for Undertow. For Netty, we are building on top of Reactor Netty, which is a separate module of Reactor. That gives you integration with Netty and Reactive Streams. And there's also the RxNetty project that some of you may be using that has a similar purpose. So if you want to use Reactor Netty or RxNetty on top of Netty, we support both of those. And also, in addition to that, we're actually working on expanding the Reactive Streams bridge to go beyond Servlet 3.1. There are already concrete efforts to bridge directly to Tomcat IO to provide a kind of even more efficient way of translating backpressure. And you'll probably hear more on this in the coming months. In many ways, this is the kind of effort you would expect in a Servlet 4 expert group, but unfortunately that's been quiet for many months now. We do think that Jetty will come on board, and they've actually been asking a lot of questions on the Reactive Streams spec repository a little while ago, actually almost a year now. So they're definitely interested and probably will come along and provide something, and maybe in the end that will translate into a Servlet 4 something, but we really don't depend on that. Now, also, we have reactive encoders and decoders. These are similar to the HTTP message converters that you may know from Spring MVC, except they're reactive and they work with the flux on the input and output side, or rather publisher on the input, flux on the output. But basically, we're translating between data buffers, a stream of bytes, and objects. And data buffer is also a new abstraction that we've created in order to deal efficiently. For example, Netty has a byte buff, so you can use direct byte buffers to minimize the copying. And this is something that we abstract. Again, this is something unique that you'll see in our framework. A lot of the libraries around Reactive that not only do they build on Netty, which means you have to use Netty, but also they expose a lot of the Netty API types in their own APIs. Here we've actually abstracted the buffer abstraction, so you can have Netty byte buffs, or if you're running on Tomcat, it's just regular byte buffers from Java. Now, in terms of the encoding and decoding, this is kind of an interesting topic in itself, because Jackson is a blocking library. Still, it doesn't have any asynchronous non-blocking option. So how do we do it? Well, on the input side, we are parsing the JSON input stream, and if that's an array, we're breaking it out into individual objects within the array, and then feeding those one by one, kind of buffering that data until we're ready to feed something into Jackson. So we're actually invoking Jackson on the input side for one object at a time, which means that we can become streaming without necessarily having Jackson to be non-blocking itself. That means extra work on our side that we'd rather not do, but at the moment it's the only way. On the XML side, actually, interestingly enough, from the same authors, there's the Alto XML library, which does do the asynchronous parsing of an XML stream and gives you nodes that you can then use for JAXB as input to JAXB, and that's what we're doing there. So there we don't have to actually parse the XML. We support server-sent events as well. This is kind of a poster child for streaming scenarios. So you can return a flux of objects or server-sent event types. And we also have the ability for zero-copy file transfer. So you can return a resource, like a regular Spring resource type, pointing to a file, and that can get served with zero-copy file transfer. So I guess at this point I can come back to the question, what happens if you return a flux of objects? Well, basically our encoder is going to take each one of those objects and stream it, in the case of JSON, as an array. As it goes through the encoder layer, we're actually breaking down the individual objects into data buffers, and then those data buffers get written out. So once it's down on the wire, there's no exact guarantee of the flushing boundaries, except when we get to server-sent events where we do have a solution to impose flushing boundaries. But the point is that it's not down to the level of individual chunks. That works pretty similar to the way it is today. Again, you may have multiple chunks, but the way to think about it from a controller perspective is that you have objects, and each object gets serialized down to bytes, and those bytes get written out. So we have also a SpringWeb Reactive module that's similar to the Spring MVC framework, except it's operating on the reactive HTTP request and response that I showed you. It's using the reactive encoders and decoders, and so on. It's interesting what came of this. You know, when we first started out, we knew that the two frameworks cannot share any code because we have to have new contracts. But in the end, there are many algorithms which are still valid. And that goes back to the beginning of the talk when I was talking about the shift from imperative to reactive. And when you use a declarative API, you can compose your asynchronous logic, and it looks very similar to the imperative, but it's broken out in chunks. So what you're doing doesn't necessarily change, right? We're just switching from imperative style to non-blocking. We're splitting up the application into chunks so that we can be neutral to handle latency without blocking and impose these kinds of boundaries at certain parts of the application. So in effect, SpringWeb Reactive and Spring MVC, they're separate modules. They don't share any code, but they share many of the mechanisms, and they're maintained by the same people. So that means us. So that means that when you report an issue or when you make a request on the side of Spring MVC, SpringWeb Reactive benefits from that. Reversely, if you're using the reactive framework and you have an issue, chances are that that fix probably applies on the Spring MVC side, and so we're going to be working on both sides. It means more work for us, but ultimately we're supporting the same programming model on top, and that's really the right way to think about it. Question? So the question is, can I mix and match? Can I have some reactive and non-reactive controllers? In many cases, you can take the non-reactive controllers or whatever you have today. They can probably be, you can just probably use them as is. As we begin, well, there may be some features that we haven't built yet, right? So for M1, we have REST support, server-side and client-side, but there's still features that we're adding, so there may be things that are still not there. The programming model is the same, and you can develop multiple applications, one in the reactive style, one in the not reactive style. But at the moment, we don't foresee doing that in the same JVM. This is something that we may change. We're sorting things out in the boot Reactive Web Starter. I mean, technically, you could run them in the same JVM, right? You could. It's just a servlet container, and you could install one dispatcher servlet and then also what we have. But we're not pushing very hard in that direction. We're not trying very hard right now until we see very concrete use cases, because we anticipate that in most cases you're taking a chunk of functionality and you're creating. You may not have to take all your applications and make them reactive. But you may take one application at a time and begin to experimenting. So in a microservice scenario where you have these more fine-grained services, each one can be written to be reactive or not reactive depending on what they do, and they share the same programming model. So that's kind of the model that we're thinking about at the moment. Okay, so we have a few examples here. Non-blocking HTTP GET. You can see at the top is kind of a method signature that implies a synchronous, but nevertheless non-blocking method. So this is an important distinction. We don't say that your controller method must have asynchronous types in the input and output. You can have blocking kind of semantics, like in this case we're returning a user, which from a method signature perspective implies that we're blocking until the user is available. We're not returning a mono of a user. But the important distinction here is that the expectation is that you're not going to block. So you can still write this style of method signature, but it must be non-blocking. You can see here we're just creating a new user. So nothing wrong with being synchronous, so you can choose basically what you need. If your method does not block to begin with, there's no need to use the async types. And then below is the asynchronous non-blocking method, alternative to that. On the HTTP post side, we have a similar example here. I talked about this a little bit earlier. You can see that you can take user explicitly as an input time, while in the second example, we're taking a mono of a user. And there's actually, by the choice of which one of these you use, the controller method in the first case will not even be invoked until the user is fully deserialized from the request body. While in the second case, we can invoke the controller method to do the composition, and then when there is a subscribe at the end, that's when the data will actually begin to process. I mentioned we have support for server-sent events, so you return a flux or an observable with RxJava with SSE event. And that's a streaming scenario. It does not involve any blocking on the outbound side. We have support for zero-copy file transfer, and the way that works is you have to return a resource that can be translated into a file. This is using a low-level Java API for the zero-copy file transfer. And of course, we also have a web client, which is an important part of this story because very commonly this is of interest when you have microservices. When you have microservices, you probably have to make some HTTP calls to other services. And you can see here what we have at the moment for M1. In this case, we're using Reactor, and we have a web client. We're performing a post. We're passing the body, which is a flux of users. So that's a streaming scenario. You can see how easy it is to do something like that. And then we're extracting the response. Now, some of you may look at this and realize that this looks a little different from the REST template. In the REST template, we had all the methods spelled out. But here, what we have is actually something that's closer to the mock MVC API that we have in Spring MVC. It gives us more flexibility, and it actually allows us to support also RxJava quite naturally. So you can see here the same example. It looks pretty much identical, but using RxJava. It's mostly using a different set of request builders and response extractors. So it's just a matter of a static import of the right kind. Okay, so we have a milestone 1 release where we focused on providing REST support for REST scenarios, including client and server side. That means that you can actually try this out for, in a kind of a microservice style application. We have JSON and XML support, as I said, server-sent events, zero file copy. That should give you a pretty good basis for doing things. We do have basic HTML rendering with FreeMarker, and separately there's a project by TimeLeaf. They're already experimenting on the side with this, and they have their own prototype. But the idea for the first milestone was to at least figure out how we do content negotiation with HTML versus REST, and that's mostly about us working out the design of the Reactive Web Framework. It really wasn't the goal to provide complete HTML support for browser applications. So probably in milestone 2, you'll see a lot more on the side of static resource handling, also supporting form posts and data binding, etc. Also, we have an experimental Spring Boot Reactive Web Starter already. So if you go to start.spring.io, it's the fastest way to try this out. Just make sure that you're selecting Spring Boot 1.4 or higher, and then just type Reactive and select that option, and you'll get started. Now, by default, the Web Starter will bring in Tomcat. But you can switch that the usual way that you do with Spring Boot by changing the dependencies and swapping out Tomcat with any of the other runtimes, right? And you will find some additional helpful instructions. So if you prefer to read a little more about the Reactive Starter, you can also go to this project here, where actually the source for the starter is at the moment. Also, you can bootstrap manually. It's not too bad. Essentially, you just have to create your application context and then a dispatcher handler. You can see at the top, we have a Web Reactive configuration class. That's the Java config that gives you all the infrastructure you need on the Web Reactive side. So it's pretty straightforward. The only thing that's left there, you have to declare your controller beans or scan them, component scan them, obviously. Then in the second section, you see where we created dispatcher handler. That's similar to the dispatcher servlet. We hook it up with the application context and create the HTTP handler that we need. The HTTP handler is kind of the common abstraction that we have between HTTP to have a handler for HTTP with reactive streams contracts. And then at the bottom is the HTTP server. This is not anything that we provide that you can download, but it is available in our own test sources. So you can, they're very basic, very simple. You can either copy them or do one yourself. The idea is that we probably will not provide these. You know, it's still up for debate. We'll see what makes sense. We're still trying to gauge that, but Spring Boot already provides a starter, and that's really the way it's meant to be bootstrapped at the moment. There's quite a bit that goes on beyond such simple HTTP server abstractions, and at the moment we really don't want to replicate that in the Spring framework. There's no need, but you know, eventually we may create some simple abstractions there for alternative use. So that's all I wanted to, all I have in my content for this session. Any questions? Yeah. So I'm not sure if I heard it fully, but the question is, do we plan to support reactive types for everything, for all the inputs and outputs?
Well, that's about feature parity with Spring MVC, so things like controller types.
Yes, feature parity all the way between Spring MVC and Web Reactive, as much as it's feasible. You know, there are some examples where it may not necessarily make sense, but by and large, 99% feature parity. How you discover controllers, how all of that code cannot be physically shared, but it's identical. Yeah. Any other questions? Yeah. Okay, so the question is, RxJava has schedulers, what's the alternative in Reactor? So Reactor has a very similar mechanism. There's a scheduling package with different types of built-in. You have all the choices, so it's very much aligned in that regard. Any other questions? Will it work with the caching annotation? I believe there's a ticket that's definitely going to be, that's definitely on the list to look at. We'll see what makes sense there. When am I going to start writing a book? Yeah, I don't know. Yes?
With the existing client servlet stuff, the Spring security stuff is based on filters. So with this, does that make a difference to how the Spring security?
So the question is, so Spring Security today is based on servlet filters. How will it work with this? I would say it's very similar to what happened in the Spring MVC side, where we could not necessarily share code. We had to create new contracts and then provide the same functionality on that side. So it's not going to be based on a filter, but it's going to be probably very comparable functionality. The one thing I would add is that we still have the notion of filters and handlers. They're not the servlet filters, but we have a web filter and a web handler and a web exception handler. So we still like the processing model that the servlet API has, but we can't use the servlet itself or the servlet filter because they have synchronous semantics. They return void, and they take the non-reactive request and response. Spring Security will build on those web filters, and that's how it will hook into SpringWeb Reactive. Yeah. What kind of reactive support in Spring integration? You guys have all the tough questions. We've done some experiments. I think the one Spring integration is probably the hardest one to answer because there's a fair degree of overlap between, if you think about Reactive Streams as a form of message passing between a producer and consumer, so publisher and subscriber in Reactive Streams lingo. But on the Spring integration side, it's a producer-consumer, right? We don't know the exact answer there yet. But most likely, it's going to be a little bit like what we showed in the keynote with Spring Cloud Stream, along those lines, where your contracts are not necessarily on the level of individual messages, but rather declaring the channel connections for the whole stream, and then making that happen underneath with Backpressure. But again, this is probably the one area which is going to require the most further work. Follow up? When we'll see something concrete, catch Gary Russell, and make sure he hears your question. So that's pretty much all I can say. I'm not sure. On the Spring messaging side, right, that's in the Spring framework, we may try and experiment for Spring 5, but again, we'll see how far we get, right? We have a release candidate in December. The priority for now is at least getting REST off the ground, which is what we did already. Then HTML, and then if we can get to the WebSocket side and messaging, then maybe we'll have some answers there too. Yeah. You would have to speak up a little bit. I heard Reactor Kafka. Oh, is there a stack trace when there's an error? Oh, when there's an exception, right. So the question is there a stack trace? Yes, there is a stack trace. So exceptions get communicated differently here, as you can imagine, because it's not imperative style logic. They flow through the same data pipeline that where we compose the logic. At the simplest level, if you think about the completable future, that communicates back an exception to you. So that's an example of where we're flowing the error through the pipeline as opposed to just raising it. So generally, when you see exceptions, I mean, at least in SpringWeb Reactive, we provide the same @exception handler mechanism. So we flow those exceptions, route them into those the right places. But generally speaking, because of the non-blocking nature and multiple threads, the stack traces aren't going to be what they used to be, where everything happened in one thread and you could trace exactly. So it's a bit of a challenge. How do you connect the stack trace? Because it's just some thread dealing with some part of the pipeline back to source code. And that's something that Reactor is already working on. There are some features already that will point to a specific part of the source code when something fails. Because typically the stack trace just shows you some message passing. And that's one of the things about event-style, event-driven applications. It becomes harder to debug and figure out. But I believe these things will improve with time. There will be more mechanisms. Right, so the question is about performance increase, how much of it? So we haven't done a lot of experimenting yet. We just believe that it will be better. But there is actually a Reactor Kafka talk, which is tomorrow, a Reactive Kafka talk. And they've done some interesting experiments already where they compared ingesting data into Kafka over HTTP. And Kafka provides a servlet, kind of plain vanilla servlet endpoint for ingesting and pushing into Kafka. And they compared that to our Web Reactive controllers doing the same. And they found, and they ran this on Rackspace with quite a good environment with fast network. And it was 3 or 4 times the throughput and much better latency. And this is before we've even looked very closely at it. So there's definitely a lot of benefit. How do we, sorry, test? How do we test non-blocking? So I should have included something on that. So in Reactor, there is a test subscriber that gives you a nice API for consuming the data from the pipeline, from a Flux. From the Reactor side, you have a specific support for building your tests. On SpringWeb Reactive side, we don't have anything specific, kind of like mock MVC yet. So that's going to be something down the line. Okay, one last question, and then we can continue. Okay, I'm not sure I fully understood correctly the question, but it is about error handling and retry, and how would it work with Reactive Streams. I would rephrase the question a little bit, because this is really not the space of Reactive Streams. Reactive Streams is mostly concerned with backpressure. Reactive Streams doesn't provide anything for composing logic. It doesn't say anything about that. So that's where Reactor and RxJava come into place, and I would say that this is one of the strengths of those libraries, is because they provide those. When you have such a functional API with operators that you can apply to the stream of data, the same applies for error handling and for retries. So those are built-in operators into those libraries. So those things actually become easier. All right, I'm going to close out, and we can continue this discussion. It sounds like a longer discussion, but thank you very much for sticking out at the end of the session, and come talk to me.